Thank you. Thank you for this opportunity to speak here. And as you see, my topic fits well into the topic of the workshop, because it's about matrix model, and mostly there is an echo. Mostly it will be about the matrices, and actually there is a quantum system behind it, the study of so-called half BPS protected operators in N=4 super Young-Mills theory. It is based on collaboration with Harish Murali and Pedro Vieira, and the paper came out a couple of days ago. Okay, super Young-Mills is a model which is under intensive study for many years. There is a big community working on it, and I worked also for maybe 20 last years on various subjects related to integrability of it. So of course here it's very schematically written action, which contains gauge fields, scalars, 6 scalars, which is important. J goes from 1 to 6, some interaction terms, like commutator squares, plus fermions, which completed to the full supersymmetric, maximally supersymmetric quantum field theory in 4 dimensions. And this is a conformal and even superconformal theory with specific symmetry, PSU 2,2/4. And maybe you heard that it's dual due to this ADS-CFT correspondence to a string, say, operators, which we study, dual to a string rotating, at least in the large limit, it's a single string rotating on this space, S5 times ADS5. And as in every conformal theory, we would like to study the properties of conformal of operators, which in this case are simply various words built out of fields in the same point. The first thing to study is the spectrum of conformal dimensions, which is just the property in correlation functions of this operator under the rescaling of coordinates. So it defines the anomalous dimensions, and so simply dimensions of operators. And another very important set of quantities is the structure constants which enter the OPE, operator product expansion. It's, as usual, believed that these 2 sets of quantities, dimensions and structure constants, define via various OPEs and various correlators, completely define the conformal field theory. Of course, there are non-local quantities, and it's richer than just that, but this is really, these are basic things to study. And there are various types of operators. Small operators consist of a few fields here. Then you can study them by ADS-CFT. Then in the larger limit, let me immediately say that all these fields are matrices, n by n matrices, where n is the number of colors. So that the action here is of the order n square, n trace, and the matrices themselves have this entropy of the order n square. So it's a complicated theory based on planar diagrams, etc. Then there are big operators. These operators can be studied in ADS-CFT, like by sigma model, 2-dimensional sigma model on this space. And integrability can mostly calculates the dimensions via quantum spectral curve. The formalism we developed for last maybe 10 years. And structure concepts also partially are calculable by integrability, all this for small operators. But say things are more complicated for giant gravitons when this dimension is of the order n, of this n. But still you can do something, and it's still ADS-CFT background that you study. And the principal interest of our work is huge operators, namely when the dimension is n square, and essentially if you compute correlation functions, they completely change the background. Say they essentially enter to the action. Yes, you have you have something proportional e to the n square because delta is n square, and of course you simply have to deform the action. It's not just computing little averages with the known action. So action is strongly influenced by operators. It's non-ADS background. It completely changes. There will be a new background which is called LLM, Lin, Lunin, Maldacena. There is a hope that it describes black holes, but the hope waned probably. You have to... No, these operators certainly are relevant to black holes, but we will consider a set of protected BPS operators, so-called BPS operators, which probably don't contain them. But in general, of course, huge operators are very difficult to study, no integrability, and you don't know what to do. But due to supersymmetry, there exists a sector of operators, so-called 1/2 BPS. Half of the symmetry is protected, about which we know nearly everything, and they have protected dimensions and protected structure constants. Namely, what is protected, that the interaction simply disappears. The coupling constant doesn't intervene, and everything happens in the free part of the action. And all the integrals are Gaussian, essentially. What you take, the functional integrals are Gaussian. The structure constants can be studied via new interesting matrix models, which is the subject of our work. And these integrals can be treated and computed using Riemann-Hopf 1+1 dimensional fluid dynamics. And this will be the main part of the talk, and sometimes they can be computed even exactly for some particular operators. Okay, so first of all, a little introduction. What are these operators? 1/2 BPS operators. One takes these 6 scalar fields and contracts by constant vector, which is light-like, 6-dimensional vector, which is light-like. This is the only condition to make it 1/2 BPS, and it's the most general operator if you take any polynomials, say, any functions of these operators. But it's very advantageous to take characters, GLN characters, based on Young tableaus. R will be Young tableaus. The length of the rows are highest weight components, and the character is computed by Weil formula. Say if you take some phi, out of these fields, constructed out of these fields, say this contraction, and take the eigenvalues, it's simply determinant phi j to hi over Vandermonde. Like this delta will always be Vandermonde of eigenvalues, which is like product of phi I minus phi j. And H, J are so-called shifted highest weights. So highest weight is the number of boxes in the row, but you shift it every time with the number J minus 1, so that you sort of make it longer. It's a convenient quantity because it's a concise way to write, for example, the characters without adding all these J's there. Okay, so why? For an example of such operators are for this Young tableau. Of course, you can write it as a Schur polynomial of traces of powers of this phi. For example, you have this kind of quantity, which certainly depends only on eigenvalues, phi I of this matrix. Then, what is nice about these operators, this is really a special system of half BPS operators because they obey the orthogonality. If you compute the average, first of all, you get a factor. You see the product of yi, yj, the vectors of two corresponding to two different operators, the scalar product. And of course, it's not zero, only the square is zero. And here you have the standard factor, which corresponds to the propagator of scalar field for a four-dimensional theory for scalars. And here the power is 2Li, where Li appears simply this dimension Li is simply the size of Young tableau. Essentially, you connect all these phi fields with propagators 1 over x square, yes, 1 over x minus y square. You count all this, the power of propagators, it's always like Young tableau. And you also have the orthogonality, which can be easily checked. I will even check it later. So both Young tableaus should be synchronized. They should be the same, which is already a good system for conformal theory because you work with orthogonal theory. You can normalize it by one or leave so far normalization arbitrary. Now the most interesting quantity, 3-point correlators. They're also protected. I will not, of course, prove for you it, but it's a well-known fact in n=4 Super-Yang-Mills theory. So if you have three such operators, you get a standard factor where you have essentially these combinations of dimensions, which we call bridge lengths, because you will see now from the next picture why we call it so. But this is a standard expression like Polyakov three-point function in conformal theory, where you have these combinations of dimensions for the powers of these four points xi minus xj for the distances in four-dimensional space. But you see the factor is standard, and the most interesting is the coefficient. And the coefficient is, after normalization, of course, it's precisely normalization of, say, if you normalize by 1, this is precisely the structure constant, which we are after, which we want to compute. Now, it's a purely combinatorial problem. I explain why. Because if you, so this factor, if you look at this picture, say this picture symbolizes traces, say the trace phi cube from out of, say, like here, trace phi square, some arbitrary combination out of this one. And for another operator, it may be 1, for another 2, say all these combinations, of course, you should sum up for each character, but schematically it's that. And if you compute the functional integral, this Gaussian integral, you simply connect these scalar fields by their propagators, like here. In such a way that, of course, there are no self-connections. It's forbidden because they are you make the point splitting of operators, and you forbid the self-contractions. You only have contractions with between different operators. And you can easily see that, in fact, this power, because for each propagator it's 1 over xi minus xj square, then what is the bridge is the number of propagators connecting, say, two propagators. Say here it's 2, so this combination will be equal to 2. For example, here it's also 2. Okay, it's what is it? Li is the overall power which you have here, and this is the size of the Young tableau, and you have these combinations. Okay, so now we are coming to a nice combinatorial problem, just counting all these contractions between various characters. It's a Gaussian integral, which we'll study, but the averages you compute with this integral are complicated. They are characters. So how to solve this problem? It's the main subject of the topic. So you can simply write an integral which counts this kind of configurations. Namely, you have here three characters. You introduce the Hermitian matrices, some auxiliary Hermitian matrices, to solve the the actual combinatorial problem. Then you have three characters depending on these matrices, and the weight, the Gaussian weight of this matrix model is this one. Namely, it's designed, the coefficients are designed so that you have no self-contraction. So Mi will never be contracted with Mi. I mean, you do weak contractions, yes? Like in every Gaussian integral, only pair correlators exist, so you just count all the weak contractions. But only different matrices like M1, M2, M1, M3, or M2, M3 are contracted. So hope I convinced you that this matrix integral solves our combinatorial problem. If there are doubts or questions, please ask.
I have a question, but that's not for this formula, but for
I know you have.
Because I haven't understood what particular operator. You defined it, but I haven't understood the definition of the operator.
Maybe, yeah, we'll discuss it later. Otherwise, I will cut.
What you are calculating, the correlation.
Yes, but
operators, but you defined it in a way which personally I haven't understood.
Okay, maybe we come later to this point. I thought I defined it, but okay. Now, for those who doesn't want to hear about n equals 4 Young-Mills, we simply solve this combinatorial problem, and this is the way to solve it. Because this is complicated, because you have matrices. You have if you try to diagonalize it, which is usual in large M limit, you diagonalize these m's, and you have the angles between these m's, here, the angular matrices, SUN matrices. It's very difficult to integrate such a combination in general. But there is a trick which I invented long ago, especially to solve so-called Potts model on random planar graphs, which consists of just decoupling this product of sum of products Mi and J into this integral. You see, if you have a product of three matrices, if before integrating over Mi you integrate over X, so you get so you have here sum of Mi squares minus X sum of Mi's. If you integrate over X in the Gaussian way, you get sum of Mi's, like M1 plus M2 plus M3 squared, which of course contains these products. It's also some squares, but you easily diagonalize trace. I mean, it depends only on eigenvalues. And here you simply decoupled by this X all three matrices. You have to separately compute this integral over each of three matrices in external matrix fields. And then later you plug this answer product of these integrals into X integral and perform the integral over X. And what is nice here, it takes the familiar form of Itzekson-Joubert Harish-Chandra integral, because you can before diagonalize the matrix M and integrate over the angle, SUN angle between matrix X and matrix M, and you express these angular integrals through the eigenvalues of X and M. So explicitly, for this integral, now we compute integral over M. Each integral is the same up to the character, the type of character, the Young tableau we compute. So the measure, the Gaussian part of the measure is here. You have the familiar Vandermonde squared of Mi's are eigenvalues of M. Then Itzekson-Joubert integral is simply given by this. And yeah, there is a Vandermonde of M, which also is here. There are some manipulations to cancel Vandermondes, and the character is simply this. divided by Vandermonde of M's. Hj are these shifted highest weights. And you see that you have, I should have started from this. I mean, this is, yes, no. So you see, I simply rewrote this, integrating over angles through Itzig-Son-Joubert determinant, and the character is already, it looks like also like Itzig-Son-Joubert determinant if you, instead of mi, you introduce log mi, yes, you exponentiate. It's exponent of log mi hj, but in principle it's a similar object, and the main part of the talk is how to compute this kind of objects in the large n limit. Okay, but then you can do the following. You can simply integrate over m's, because everything is Gaussian here. You have Gaussian integral, Vandermonde squared is some polynomial, you have determinant of exponents. So if you can simply integrate over each eigenvalue, mi, and you get this integral. Determinant of already a single integral dm, because all the integrals are the same. It's a single integral under determinant of x. Here you have xi and hj. And in fact, this is nothing but a Hermite polynomial. This is a generating function for this Hermite polynomial. So you have Hermite polynomial with the label which is shifted highest weight, and xi enters as the variable of this polynomial. And you have to take the determinant. Everything is antisymmetrized here. You have determinant. So eventually you get this nice determinant, which is Slater. I mean, it's a part of Slater determinant for free fermions in a oscillatorial potential. Yes, what is the Vandermonde? What is the determinant of Hermite polynomials? If you add e to the minus x square, then it will be literally the Slater determinant. I will call it Slater determinant, although exponents I don't include here. They are somewhere in the integrals. And eventually, finally, our integral becomes one matrix model, but with complicated weights. You insert 3 such Slater determinants divided by Vandermonde of x. This determinant divided Vandermonde of x. It is defined by Young tableau, because h and j, where n is 1, 2, 3, each has its own Young tableau, or its own representation, and you have to simply integrate them with this Gaussian measure. You can even write it as a matrix integral, but I wrote in terms of eigenvalues. So this is the main object of our study, which solves the combinatorial problem which I mentioned before. So the question arises how to find it before we integrate over x, how to calculate these complicated objects. And actually, if somebody knows about it more, I would like to hear. I tried to look through the literature. I didn't find anything advanced on the topic. That if you have large n, if you have a smooth Young tableau, and if you have some smooth distribution of eigenvalues rho of x, and density of x, how to compute this quantity in terms of the density of highest weight of Young tableau and the density of coordinates x. So this is the problem which arises, and we have somehow to deal with it. So again, this is clear. I hope it's just formal exercise. And now I proceed with studying of this quantity. And first of all, studying the Slater determinant. First I explained the 2-point function. Of course, as you understand, here we have 3-point function, which amounts to computing the structure constant z, but you could have two-point function, which will be exactly the same but with two q's. The q of one Young tableau, q of another Young tableau, and already we have to show orthogonality. Namely, we study the two-point function, which will give us the normalization of this coupling. Because the structure constant should be normalized by square root of products of two-point functions, as it follows from OPE. So the normalization constant is essentially this one, where z are two-point functions. And if we compute them, it's just simply the integral over q1, q2, the same integral but with two q functions. You see that it's simply a product of determinants of Hermite polynomials integrated with their own measure. And of course, each polynomial meets the same variable in this determinant. And by orthogonality of Hermite polynomials, you simply get product of along the Young tableau. First of all, you get that both Young tableaus should be equal, and here you have product of normalization factors of Hermite polynomials along the Young tableau, with Hj being the shifted highest weights. So we know explicitly the normalization for our structure constant. And now a more serious problem, how to compute the structure constant, where we have these three functions. First of all, we start from each q, from individual q's. And as I said, they look like Slater determinants of free fermions. Namely, you take the oscillatorial potential and you fill some levels and some you leave free. And it corresponds to the pattern of filling. This pattern corresponds to the Young tableau in a very simple way. Each level labels the length of Young tableau. Forget, sorry about these blue things. I will tell what it is, but Young tableau is red. For example, if you have Young tableau with n rows having equal highest weights k, so you just don't fill first k levels and you fill the next n levels. This is the Slater determinant, the object which we compute Slater determinant for this filling. Then, for example, here we do the same. We also have first k levels not filled, but then we fill every even level. Then this is this Young tableau. And here we fill only even levels. So we jump over each odd level. And this is this red Young tableau. But what is blue is simply shifted highest weight. We shift the first row here by 3, this by 2, this by 1, by 0. It's just shifting by number, because it's a very convenient definition of this shifted highest weights for us. Otherwise, red are Young tableaus. Okay, and then, for example, for rectangular, we call this rectangular Young tableau. So just Q rectangle is this determinant. You see all h's go one by one in numbers, but all of them are shifted by k. And there is a beautiful representation, which is, I don't know exactly to whom which is due, maybe Brizan Hikami, maybe somebody else. I couldn't find out exactly. But I found it in the work of Mazeng, and I forgot the second name. Ogawa, I forgot. But it's a very nice representation of this Slater determinant, this one, is the shift, that you have the Gaussian integral over y, and then you have the product of x's, this x alpha from 1 to n, minus yj, eigenvalues of this auxiliary matrix integral, which for which we have, it's integral for k by k matrix. So there are k eigenvalues, which is nice. You immediately can write it in the saddle point at large n as some linear relation, integral equation between x, distribution of x and y's. Similar maybe not known, I don't know, representation we found for this case when only every even level is filled. And finally, the simplest is this triangle, because it is simply equal to Vandermonde x square when you have only even powers. Of course, it's Vandermonde of x square, going from 0 to up to n. And when divided by Vandermonde, it's this nice quantity, which is simply product of xi plus xj, yes. These three cases are relatively, I mean, they can be studied maybe better than arbitrary filling of Young tableaus, and sometimes even analytically tractable. Namely, for this case, for triangle, we get interesting structure constant for 3 Young tableaus of this type. If we study it in the large n limit, I mean, in principle, this is the exact expression for such structure constant for 3 equivalent triangles. You have standard Gaussian integral with Vandermonde square, and also you have this ratio of Vandermonde square over Vandermonde, which gives you this product of xj plus xk. Power 3 comes because you have three such operators, 3 such Qs. And this actually already reminds very much the model, ON model on so-called ON model on random planar graphs, long ago introduced by Kostov, and actually in the large n limit we can write the saddle point equation, just simply varying with respect to each k, the log of this expression, and we can rewrite it through a nice Riemann-Hilbert problem for resolvent. The resolvent is simply this, and that we can solve. This is a solvable Riemann-Hilbert problem, probably first solved by Einar Christiansen, who considered this Kostov's model. It can be solved in elliptic functions. So theta's are Jacobi elliptic functions, and where x of u, so it's g of x, which is parameterized through elliptic sign as a function of u, and g is also a function of u, and so you have the parametric representation of this solution. And actually you can use this solution to compute the action. Of course, what we compute is e to the log of z at the saddle point, and the saddle point is defined by this solution, which contains the density. Of course, if you take the jump on the cut, the imaginary part at the cut for this function. And if you compute the corresponding integral, which you can do numerically, it's quite complicated elliptic integral, so integral of elliptic functions, but you can do it with virtually arbitrary precision. So we consider it as an analytic solution, so you get this kind of structure constant, yes? Or the structure constant is e to the n squared times this number, yes? So it's probably the only known computation for such three big Young tableaus, 3 huge operators. Of course, it's just a number. You don't have any parameters, unfortunately. But for the other 2 models, like for these 2 models, for these 2 types Young tableaus, we have this parameter k over n, essentially, the large k and n limit. And it would be very interesting models to study them in as functions of this ratio. And I can only say that I will show you the corresponding Riemann-Hilbert problems, which we were not yet able to solve, but maybe they are solvable. And one comment that this is only a leading saddle point. There is a continuous amount of saddle points. There are many solutions. This is one-cut solution, as you remember, in one matrix model. But you can have two-cut, three-cut, etc. solutions which have which are subleading with respect to this leading saddle point, or they can contribute only to the pre-exponent. So you have e to the n square times this number, but in the pre-exponent you can have powers of n, and of course if you want to compute them you have to take into account the subleading saddle points, but this is the leading.
Sorry, they are subleading in the large n for
yes. With respect to the powers of n, yeah, you have leading exponential e to the n square times number, which we computed, and then you have n to some power, etc. Okay, so this is for this solution. Now, for the other more complicated cases, trapezium and rectangle Young tableau, we call it, to be precise, we call this Young tableau trapezium, which is even field levels starting from kth. And this is triangle, and this is naturally rectangle. So we can, we have some numerics built on simply relaxation, simply finding the minimum of saddle point in the action. So you have various ratios between k and n, this parameter k over n. So you start, for example, this is when the ratio is 2, 1, 1/2, etc. And these are eigenvalues as you find them. There are many eigenvalues. You find the distribution, the density of eigenvalues in this rho of x. Rho of x is the density of eigenvalues x in the saddle point. So in principle, knowing it, you know the answer for the structure, for the corresponding structure constant. And finally, for example, numerically, you get a perfect coincidence with the triangle case when k is 0. Red is our analytic curve, and this is numerics. So things work smoothly here. And just to mention that for triangle we have elliptic solution, this red one, but we can write saddle point equations for trapezium case and rectangle case. And okay, I don't write here the details. All these ratios are somewhere in the symptotics of this function, but we have to solve this complicated Riemann-Hilbert problem. Maybe it's solvable via algebraic curves, but this is certainly to start and to finish yet. Okay, and now what to do with generic Young tableaus, with generic 3 operators, but with smooth Young tableaus, I mean big Young tableaus which are not crazy, like most of the highest weights should be of the order n. That's the problem. And then I have to give you some introduction into what we call Harish-Chandra-Isaacson-Joubert integral and its relation to fluid dynamics. It's a topic known for maybe 30 years, but it's good to remind it. So this integral is simply, as I mentioned already during the computation of structure constant, it's simply this integral. You have integral over SUN group for the group matrix omega, and you have omega A, omega dagger B, where A and B is the system of eigenvalues. And computing this omega, you get this famous expression up to constants, up to normalization, which I always drop here for the purposes of the talk. But there is a simple n-dependent factor here. So you get this determinant e to the aibj, j, sorry, it's not I, aibj, and divided by Vandermonde A, Vandermonde B. You have to study this object to solve our problem. What to do? And it's a complicated object. And in these works, it was reduced to a beautiful 1+1 dimensional fluid dynamics described by, so our integral is described by the following action in the large N limit. So you have the density. You have to introduce the auxiliary density, which depends on t, and develop it from 0 to 1. Then you have the velocity of this density, and you have also this term rho square. And you have some boundary terms, which, for example, this is this van der Waals, and this is, you have an extra x squared term here by some reasons. So the statement is that if you minimize this action, if you find the minimum with respect to this two-dimensional, or already this function rho of xt, with certain boundary conditions, you plug it into this action and you find the value, the leading value of this integral of the order e to the n square, which will depend on these boundary values rho a and rho b, which is a rho at t equals 0 and rho b is rho at t equals 1. But you have to solve the whole dynamics, and this is known to extremization of this action gives you the 1+1 dimensional equation for inviscid fluid, Euler equations, Euler equation plus equation of state, and with certain boundary conditions. So equation of state is the pressure is proportional to minus rho cube, so it's quite exotic. It's minus sign here. Then you have, as I said, rho A and rho B given as the initial, it's your data, density of A's and the density of B's. So you have to compute it as a function of these two densities. And the saddle point equation, the extremization of action simply renders so-called Riemann-Hopf equation, which actually packs into it both the state equation and the Euler equation into one complex function. So if you plug it in, you get two equations. One is essentially this, another is Euler equation. Now, so this is a solvable equation normally. It's just first by characteristics method, and the solutions are well known, except that it's very difficult to understand which solution you need. It's easy usually to solve it if you have initial conditions like the velocity and the coordinate, the velocities and the density at the beginning, the distribution of velocity, this v and density. Then the solution is really simple. But in our case, it's more complicated. It's sort of boundary problem. You have only densities at the beginning of this flow and at the end. And this is a more complicated problem, which we will study now. So the endpoint velocities, for example, are given by simply this variation with respect to endpoint rows, velocity at time 0 and velocity of time 1.
Sorry, question. So the velocity is not constrained by the boundary condition? Like there is no... What's the value of...
The velocity...
what's the value of v at the boundary?
Actually, the problem as v... our problem is that we have only densities. So you have two... For this differential equation which you have to solve, it's in fact the second order equation because you have two equations, yes, if you plug in this function. So you have to have two boundary conditions, either for example one of densities and one of velocities, or density and density at the end, or velocity and velocity. Any two functions would do to fix the solution of this equation. Did I answer?
I'm not sure, because so what I don't understand is so there is a V in you know the second line. So it's the
A and B.
no, sorry, the first line there. So there is a V.
Vxt is some auxiliary velocity. You have to solve this equation with particular boundary conditions. Boundary conditions are rho A and rho B. The density at the beginning and at the end. They correspond to densities of.
But when you have this action, this fluid action, and you have V, there is no condition on V at the boundary.
You cannot give four conditions at the boundary, only two. Either you give rho and V at t equals 0, etc. You have to fix two functions. Our case is sort of difficult because we have to fix two rhos at the ends, to these two. But the velocities can be computed later. If you find the solution, you simply compute them this way. Okay, then what is now the calculation of this the full structure constant using this Itzhak-Son-Zubair hydrodynamic representation of Itzhak-Son-Zubair. So again, we go back to this 4 matrix integral, one over x and another 3 over m's. As I said, we can integrate here over angles and get Itzhak-Son-Zubair, and character also looks like Itzhak-Son-Zubair, and recasting all this in terms of eigenvalues of x and eigenvalues of m, you come to the following. So you remember that d mu of x is just the Gaussian measure. It's e to the product dx, e to the x squares times van der Waals square. Same for d mu here of each of these 3 matrices. And then you have the sort of a convolution of two Itzhak-Son-Zubairs. First one is for this integral, for the angle between x and m. And second is simply the character, which looks like Itzhak-Son-Zubair. Both can be in principle computed via using fluid dynamics of the previous slide. And then a bunch of van der Waals due to various normalizations. So these are simple things, explicit things as functionals of density. But later we have to find the saddle point. We have to calculate these integrals by saddle point and mu. This will give 2 problems for each integral of fluid dynamics, and then we have to plug it in and calculate the saddle point in x. Quite complicated scheme, which I tried to reflect in this picture. So you have x, this variable in the center. Then you have, at each of these legs, you have, of these 3 legs, you have the convolution of 2 Itzhak-Son-Zubair integrals, this and that. This is for character, for this Itzhak-Son-Zubair, which depends on highest weights, Hn, and this is for this previous one. So you have to say, if you start from this end for each leg, you start from the given Young tableau, then you evolve the fluid, which brings you to the eigenvalues of m, so it's from x to m. Then you have to jump to this one, to this I, and the variable changes, as I said. It becomes Itzhak-Son-Zubair, but with minus log m. So you kind of have to glue these 2 flows, then evolve the flow till this point, and then they meet all the flows, and they have the same distribution of this x variable. So from m to x, but x is the same. So it's roughly this scheme. I have some, maybe it's not too much for the talk, but I simply listed all these steps. For example, here the gluing conditions are in fact the result of saddle point integration, and they simply relate the velocity here, at the beginning here, and at the end here. This Wn is the velocity here, and Wn is the velocity there. You see, we cannot just give you density here. We just can relate the velocities. So it's sometimes you use densities at the as the initial condition, simply use velocity, say that h corresponds to the density in this fluid, the initial density, and then you glue the velocities together, then you go here and you finish with the same density. And then you plug it into the saddle point here, which looks also quite simple. It looks like this saddle point equation looks like how it's called, also Riemann-Hilbert equation, which relates three velocities at the ends here, Vn, to the density here. Altogether, it makes the full system of saddle point equations, which you can start solving. And then if you compute, you can compute the action using these densities if you find them. But it's difficult to do it in continuum. All these are continuous flows. And what we do, well, first of all, a few just technical comments that it could have been simpler, all this scheme. For example, for this flow, you have a nice solution in terms of inversion of a certain function. So if you have this function f, which encodes the velocity along the flow and the density, you write these functions g of x, which is essentially initial condition x plus this function at t equals 0. So it encodes your initial conditions. Then the final function g minus of x is x minus f of t equals 1. And due to the simplicity of Riemann-Hopf equation, you can simply show that these two functions are inverse to each other. As simple as that. So it's wonderful. You avoid all these complications with flows. You simply inverse the function. The problem is that this function is generically defined on a very complicated Riemann surface with many sheets, cuts, auxiliary cuts. It's not simple at all, even for simple Young tableaus, initial Young tableaus. So it worked for some cases. I will tell you for one of them, but generically it's really very difficult to figure out what you need. Moreover, even for this combination of two flows, as I said, this actually defines the Slater determinant. So for Slater determinant, you can also get similar equation. It's a convolution of two inversions with some change of variables. You get this very nice equation, nicely looking, for the computation, direct computation of Slater determinant, for generic distribution of Young tableau and the labels of polynomials and of arguments of x's. But again, the problem is that it's very difficult to guess if you make inversion. If you do inversion on very complicated Riemann surface, you don't know on which sheet you will get to when you do this inversion. Okay, but maybe this approach one day will be more advanced. But in the absence of it, we simply want to follow this flow, literally follow the flow of these particles, and we should discretize for it, discretize the equation. And discretization, the best discretization is actually another integrable model, Calogero-Sutherland model, which simply has these equations of motion. So that these xi's are already individual particles in this fluid. We defined the fluid as a collection of these particles with n particles with coordinates xi. And this equation is easily solvable. Again, I'm not sure, and I think it's already was given by Luzhenetsky and Perelomov in the 80s. So it's a nice solution. If you know the initial velocities and the initial coordinates, you simply have exact solution in terms of all these x's at any moment t are eigenvalues of this matrix, which is built on initial velocities and initial x's. Simply, if you have a finite n, even big, it's just a piece of cake to find the eigenvalues.
It's very singular, this equation.
It's singular, but the solution is not too much. I mean, of course, you have to do so-called relaxation. You start from known solution, then little by little you...
And how, for example, if n is equal to 2, how the solution looks like?
It's also here. I mean, it looks like that. It's not... this is generic solution, but of course we want large n.
What is P again?
P is the matrix which you plug in here. V is here.
So,
X is here.
P is some initial conditions, right? What?
The X and V are initial conditions.
Value problems.
Yes.
So as follows. If n equals 2, it shouldn't be complicated.
Shouldn't be.
And so, well, can you write it explicitly?
Not immediately, but you can.
Just because in examples it would be better understood.
Maybe it's my fault. I should have written, but okay, we can discuss it later. But it should be very easy as 2x2 matrix. Okay, so examples of numerical solution using that. Again, we try to just to model by Calogero-Sutherland the whole fluid flow in this scheme which I gave you for the structure constant. A nice example is, for example, we impose in the middle node the semicircle distribution, then we follow the flow in the opposite directions. We take symmetric flow, like it comes to the same Young tableaus. And so it's, you know, that semicircle can be actually we can use the exact solution of Calogero-Moser as just a second to pronounce this phrase as the zeros, so zi's of t are coordinates, and if you follow the zeros of the zero of this Hermite polynomial with particular b and a, which you can calculate, simple a's and b's, you will get the solution. And you can start from this distribution and this axis. What?
No, I think we should probably wrap up.
3 minutes. Yeah, very quickly. I show at least the result. So we do this, and here it's analytic. Here we solve it numerically. Essentially, you get the following. Here in this fluid you get exact solution, then you come here, it goes into complex direction, there are some shock waves, etc., but somehow it comes to a nice Young tableau, to the real distribution, and here is the resulting Young tableau, looking nicely, smooth, etc., so at least we know solutions for these Young tableaus. Okay, and we can, it's already very quick, for these more general Young tableaus, it's more complicated, but can be done by so-called relaxation method. For example, for trapezium and rectangle, numerically we get this, so you start from t equals 0 from this distribution of highest weights, you go through this flow to t equals 1, then you continue from 1 to 2 is another flow, so it goes to complex, the distribution of eigenvalues goes to the complex plane, but we end up with a nice density for Young tableau, for particular Young tableau. This is a rectangular Young tableau. Okay, and this is the last slide before the conclusions, but here I'm only learning this LLM, Lin-Lunyan-Maldacen geometry, which in principle solves, for this huge operator, solves the problem on the gravity side. So these operators or their correlation functions amount to analyzing the following 10-dimensional gravity solution. Sorry, I'm sure for many it will be some empty words, but you can study this kind of operators and their correlation functions in the following way. You find the gravity dual which is built in LLM case in the following. You take Young tableau, you turn it by 45 degrees like that. Then you, from each corner of this Young tableau, you trace a line and you color it in this way. Black, white in the obvious pattern, yes? Then, according to this pattern, you draw these concentric circles. Like if you make a cut here, it will be the same as there, the same pattern. So you can easily find the coordinates of these rings. So this defines the domain D, dimensional domain D. Say black, D is black, for example. Then you build the following metric. It depends on.
Maybe you should catch it very quickly because
1 minute. I'm only 1 minute late, but
questions.
So it depends on one function z x1, x2, y. Conclusions are very short, and you solve the six-dimensional Laplace equation with boundary condition on this plane, which is called LLM plane. And this function z on the plane is plus minus 1/2 according to white and black. And then you get this 10-dimensional metric with this symmetry pattern. Z enters here and this x is two-dimensional plane exactly, etc. There are 10 coordinates. Okay. There could be more general geometries related to these areas, but okay, this is about just the comment how to calculate 2- and 3-point functions from this geometry, but now it's discussion. So structure constants of half BPS operators of n equals 4 super angles expressed through relatively simple magic matrix integral, solvable via saddle point approximation and integrable fluid dynamics for huge operators. For particular huge operators, we found some solvable cases, and maybe algebraic curves can help to solve many of these cases. Of course, main question is how to map it in 3-point functions into LLM geometry, which I showed in the previous transparency, and deformation to more general unprotected operators, of course, is very interesting from the point of view of black hole physics, but you have to study already the interactions, the slightly more complicated operators, which implies the interactions in Young-Mills interactions among them. And maybe there are new kinds of quantum integrability on such LLM backgrounds can be found. So then the quantum effects, double scaling, study of this matrix integral for various Young tableaus. It's a huge space of parameters. There could be interesting phase transitions related to gravity phase transitions, etc., etc. So that's the end of the talk. Thank you.
Thank you very much for the nice talk. So, there are any urgent questions from you? Otherwise, we can even. There will be a coffee break for 25 minutes. So.
Well, I have an urgent question. So, can you still define your operators? What is the problem that we were solving?
Define in n equals 4?
Yes.
I said it's. I think I did it I really showed it in detail. What can I do?
Show this formula,
okay,
and then I will ask you what I haven't understood.
Okay, so there is an action.
Well, that's something very general, right? And then you said something about QH operators and written some formula where there was a representation, something little bit.
Okay, but of course you simply have this part of the action, nothing else.
That I understand, but I don't understand something after.
Okay, that's already good, a good beginning. I thought I have to go into details of n equals 4 Young-Mills, but now you have 5 scalar fields.
Well, there are 6 of them.
So it's 6 scalar fields.
Well, but how this formula is written? There is some index, there are 6 of them.
Dot means that it's 6-dimensional contraction of vectors. Yes, you have 6 vector y.
You have 6 vectors y.
You have 6 vector y and 6 vector of fields. Fine.
What is I?
I is now I see your point, and you are right. It's not the same I as here. Yeah. No, sorry. What I do say? Of course, I is the label for. So no, everything's fine. I is the label of operator. So you have 3 Young tableaus. You have 3 such Young tableaus. So dot is among 6-dimensional vectors, but I is the label. You have 3 x points, I equals 1, 2, 3, and 3 Young tableaus. Sorry that it's not the contraction of i's. I should be written.
What is n? NR, what is it?
It's the normalization factor which depends on Young tableau.
Factor, so you can forget about it. So phi is a matrix in some particular representation, right? Phi are 6.
Phi is Hermitian matrix.
Hermitian matrices in some particular representation, right?
Hermitian matrix. N by n Hermitian matrix.
Is a representation, right?
Then you put it inside the character, which is trace in particular representation. That's true.
Okay. Now you can consider the correlator of operators, matrices in different sizes, right? So it's the matrix of some size, which is dimension of representation.
N by n.
N by n.
Yeah, phi is n by n, but then you write characters like that. Yes.
Phi is n by n. That's fundamental representation.
Okay, then you take character, and it can be any. Here it's particular character, say for this Young tableau.
So how the representation? Phi is a fundamental representation, right?
Okay, this is Hermitian matrix inside each trace.
Yes, in fundamental representation. What is R then?
R is the Young tableau. Say this is for this Young tableau, for this Young tableau. This is the character.
Well, frankly,
I don't understand what you don't understand.
Okay, phi is some particular matrix n by n in fundamental representation, right?
It's it's n by n Hermitian matrix.
I don't see how R enters in the right-hand side of this form.
This is a Schur polynomial, which depends, of course, on the Young tableau. It's just an example. This is in terms of eigenvalues. If you take h's according to this formula, you get this. Yeah, I can't say it clearer.
Okay, thank you again. So